Hello everyone, welcome to Semiconductor Device Simulation. This is Lecture 5, 2D and 3D Problem. In this lecture, I'm going to extend our problems from 1D into 2D and even 3D. So first, I'm going to talk about the Poisson's equation in 2D, as well as the Drift-Diffusion Equation, and then I'm going to show you some code demonstration for how to solve 2D Poisson's equation. And in the end, I'm also going to introduce you a semiconductor device simulator that is called SEMIDV, which can solve the 2D Poisson's and the Drift-Diffusion Equation. So far, we have discussed how to solve 1D problems, but real devices is 3D. However, it is very hard for us to directly use 3D matrix to solve it. Therefore, we need to map those matrices into 2D array. Let's first look at Poisson's equation. Here I'm showing you a very general expression of Poisson's equation that can be applied to any dimension. And since now we are focused on 2D problem, we can rewrite this equation into its 2D form, including this rho x and the rho y terms. Then, as we have already learned that we can use finite difference approximation to rewrite all these derivatives, which can end up into these two terms. And then now we can write down our Poisson equation in 2D using finite difference method. Here for simplicity, I just drop all these chi terms. But in reality, you also need to consider them. And then if you want to solve to the nonlinear Poisson's equation, let us just look at this general form of the nonlinear Poisson equation. And what you need to do is just replace all these divergence and gradient with those finite difference equation we have derived. Similarly for our drift diffusion equation. For continuity equation and under stubborn variable method, we can also get some form as a divergence and a gradient in it, which is very similar to our Poisson equation. And then we can also rewrite this equation using finite difference method and get our finite difference form of continuity equation in 2D. Then now we know how to write down our finite difference equations for both Poisson and the drift diffusion equations for 2D or even 3D problem. Then the question is, how can we solve it with codes or computer programs? As I say that, it's very hard for us to deal with like 3D arrays. Therefore, we need to map them to a 1D vector. So in our 2D problem, here our EC in this 2D space can be written down as this 2D array. And what I want to do is to reshape this 2D array into a 1D vector. So the first n elements in this vector will corresponding to the EC in the first row, and the second n elements will be the EC in the second row. So in total, there will be n groups of all these EC, and the length of this vector is n by n. Now we need to find out some way for us to fill out our 2D finite difference matrix. So let's take EC at position I and J. So for the diagonal term, it corresponding to EC at IJ. So if we look at this finite difference equation, the diagonal term will be minus AI minus BI. And for EC j plus 1 and the EC j minus 1, they will be next to our diagonal term. So you will find bj minus 1 and bj plus 1 here. And then what about EC at I plus 1 and I minus 1? So let's recall our reshape EC 1D vector. You will see that if you have to find I plus 1 and I minus 1, it will be plus n and minus n elements far away from our current EC I and j. Therefore, in this row, you will be able to find them at plus n and minus n away from our diagonal term. So they will be filled in our ai minus 1 and ai plus 1. Now I'm going to show you the simplest way to implement a code to solve a 2D linear Poisson's equation. And although I only solve a linear Poisson equation, but you will be able to apply the same method to nonlinear Poisson and also a coupled Poisson drift diffusion equation. And as you can see on the previous slides, we will want to be able to track all those positions of EC after we reshape it. But it is very hard to do it by hand or your brain. So here I'm going to show you the simplest way and the dumbest way to do that. I hope you can find some other clever way to help you accelerate this procedure to find the index of those I and j elements. So here what I do is I create a function called findIndex, which taking the index of I and j. And let's say that if our I is smaller than 0 or greater than our nx, where nx is the number of the x point, or j is smaller than 0 or larger than ny, and the function will return -1, which is telling us that, okay, we have reached the boundary. So we need to deal with the boundary condition. Otherwise, it will just return I times ny plus j, which if you look at the number it returns here, it is corresponding to the EC position in our reshape 1D vector. And then after we have this find index function, we can just use a loop to fill in our finite difference matrices, both the left hand side and the right hand side. Again, this is what I call the dumplings weight. You can think of that if you can find some more clever way to do this, so it can be faster. And first, I will find the index for I and j. Then I will fill out the diagonal term. Then now I'm going to find the index for I minus 1, I plus 1, j minus 1, and j plus 1. And if it returns -1, that means, okay, now I will need to deal with the boundary condition. Depending on whether it is Newman or Dirichlet, I will add different terms to right hand side or left hand side array. Then after fill out these finite difference matrices, I will be able to solve for EC. So here I'm showing you an example to calculate the depletion region in a PN junction. And here is the doping profile I gave it. And you can see that it gives you a 3D surface plot of EC, and it follows what we think a PN junction depletion region will be. And if you remember the boundary condition I gave in the previous slides, for this, and this boundary, and I gave them Newman boundary so that the derivative of EC here are 0. And for this boundary, I assigned EC equals to 0, so it is the Dirichlet boundary. Due to the limitation of this lecture, I'll be only able to demonstrate you the code for 2D linear Poisson equation. However, if you want to learn more, I'm now introducing you a new tool which is called SEMIDV. It is a 2D Poisson drift diffusion simulator that I developed using Python. So if you want to use it, you will need to install it using pip and then import SEMIDV during your Python simulation. So what it does is very similar to what I have told you in this class. It will do the gamma iteration to iteratively solve the Poisson equation and the drift diffusion equation. I also introduced some other new features to deal with quantum problems. In SEMIDV, it is very simple for you to set up the device structure and boundary conditions to calculate the results such as band structures, currents, and capacitance of a device. To learn more about SEMIDV and use it for your own device simulation, you are welcome to check out my GitHub to download the source code and the menu. You can also take a look at this paper, which is talking about the physics and the equations in SEMIDV and the example of using it to study the advanced transistors.